Right, so let's look at this tutorial. So we're going to have a look at modulation, and first thing we'll have a look at is adding some noise to our signals, and then we'll look at AM, FM, and then we'll look at how we modulate binary signals. So the first one we're going to have a look at is basically how we add some noise to a signal. So this will add some random noise of a certain amplitude, and we're going to be using the signal library here, which comes from the Skype library. So let's go and integrate that. So we'll just start that, and we'll just call that tutorial 01. Paste that in. Okay, so fairly simple. We're just going to plot it. So we get, in this case, we've got a sawtooth wave, and just get rid of that. Okay, so it's going to be a sawtooth. We'll add some noise. So in this case, the amplitude of the noise is 0.1, and then we'll just run that. See how we go. Okay, so you can see our lovely sawtooth has been affected by the random noise, and obviously if we increase the value, the amplitude of the noise, then we'll see it'll be affected by it even more. Okay, so you can see there it's affected it quite badly in this case. Okay, so we'll set up a page that you can actually have a look. We'll implement this program a little bit later on, but this is the example here, and we're adding in, there's some noise. So a noise value of 0 doesn't add any noise at all. There's a triangular wave, sine wave, square wave, and so on. If we go back to our sawtooth and we add in 0.2, then we should see our lovely sawtooth has been affected there. So as we've seen in the previous tutorial, when we look at a sawtooth, what we get is we get the fundamental, which is 5 Hz in this case, then the second, third, fourth, and so on. And let's see what happens when we add a bit of noise. We still see these peaks, but here along the bottom now we've got the noise. Okay, so one way we could do this is to actually filter out these peaks from the rest of the waveform. So if we increase it a little bit more, we'll see the noise threshold will actually start to increase, and we see up here it's starting to lose a bit of the resolution there. Okay, so this is the signal plus our noise. Okay, so there's what we get with 10 Hz. So the next one we'll have a look at is amplitude modulation. So with amplitude modulation, what we have is that we are able to add on we have a carrier frequency and we have a signal frequency. So the amplitude itself actually varies with the signal's frequency. Okay, so we'll just get that integrated. So let's check. And let's try and import it again. Okay, this time it came in. Okay, so we just reformat a little bit. Sometimes the PDF can lose a bit of the formatting. That's that. Okay, so the carrier is equal to 1 plus m. M is the ratio between the carrier frequency and the signal frequency. Okay, so we'll go ahead and plot that. Use the extra space in there. Okay, and then we can define a value of m. So we'll go for 0.3 there. And we'll make that y. And there we go. Okay, so we have amplitude modulation. So we can see the shape of the signal here. And then this is the shape of the carrier. So if we increase the value of m, we should see that it will increase the carrier signal. Okay, we can see that's much larger now. Okay, so again we've set up a page that you can have a look at. It's here. Okay, so this is FM, and there's 0.3. We can see there's the modulation. And if we increase that to 0.6, we see some much deeper modulation there. So what we'll do is we'll make that 10 and the signal frequency of 2. And we can see the shape of the 2 Hz there, and 10 Hz is the actual carrier frequency. So one thing to notice is that we have a peak around 10, and then we have side bands plus the signal frequency. So if we go for 5 here, we see here we have one at 15 and one at 5. Okay, so the modulation gives us the single frequency. The biggest frequency is the carrier, and then we have 2 bands around the signal frequency. One at 5, and it folds itself also up into the higher band there at 15 in this case. So we can try 20 and 10, and we should see that will shift us up to 20. And then we have a single frequency here at 10, and then another one at 30. Okay, we can actually create a Fourier transform and analyze the signal. So again, if you add that piece of code in, then you should get the same graph as that we actually see here. And now we have FM. So for FM, in this case, this is the equation that we use. So this is the signal frequency here, and there's the carrier. So we can just create this. I'll just tidy it up a little bit. Okay, we just added a little function in here to cope with the FFT. And here's the main code here. So there we go. And we're just going to show that. So we'll give that a try. Okay, so there we go. So this shows the frequency modulation. For a sine wave, we have a certain carrier frequency and a signal frequency. So if we vary the signal frequency to 4 Hz, we should be able to see the effect that it has on there. Okay, so you should see that it's getting thinner around here and then less thin there. So the effect that it has on the frequencies actually depends on the value of m that we use. So let's increase m to make it 0.8. And you can see it much more noticeably there. There's the sine wave is actually in there and is varying the frequency. So again, you can actually have a look to see the FM here. So this is a carrier frequency of 20 Hz. So we'll just drop that down to 15 and we'll make that 5. Okay, so you should be able to see that the frequency varies there. Okay, so you see it's getting thin there, and then the period is obviously longer there. Okay, so now what we'll do is we'll have a look at amplitude shift keying. So with amplitude shift keying, we'll just take that. So we're going to set up an array of values and then use this array to be able to determine if we have a 1 or a 0. Okay, so we'll just copy it from here. And we just use the same one as before. But we'll just get rid of the extra bit of code. Okay, so in this case we're setting up a bit array and then we're actually copying that in for our modulation. So DD becomes the repeated pattern, and then what we have to do is then use that bit pattern to generate our modulated sine wave. Okay, so we take a bit pattern, we then convert it into a repeated pattern, and then we have the value of y, which is our result from our sine wave, which is modulated. Okay, and there we go. So there's a amplitude shift keying. There's a 1, a 0, a 1, and a 1, and a 0. We can see here that the peak frequency is still around the 10 Hertz, but we have a little side lobes off there now because of the discontinuity it creates between the sine wave and then the flat there. Okay, so that's the type of pattern that we get, and again you can actually have a look at what that looks like from the web page. Okay, so there it's there. Change the frequency and we should see the frequency move down to here for the main fundamental frequency for that. Okay, so the next thing we're going to look at is frequency shift keying. So with frequency shift keying, what we can do is to we can define the delta in the frequencies. So in this case it will move the frequency on 5 Hertz and it will reduce it by 5 Hertz. So if we move it on 5 Hertz, it's a 1. If we move it back 5 Hertz, then it's a 0. So in that way we can create the different frequencies that we need. Okay, so let's go back here. We'll just paste it back into here. So this is us defining our 1s and 0s for the frequency difference. So all it's really doing there is to be able to, when it's a 1, it moves on 5, minus 5 means a 0. Okay, so let's try and plot that one. There we are here. So our pattern was 1, 1, 0, 1, 0. So we can see here we have the higher frequency, that's the 15 here, and then the lower frequency, that's this one here, which is 5 less. We don't actually see 10 because 10 is not included. And then we get some side lobes around there because of the discontinuity again between the two frequencies. Okay, so we should be able to have a look at this on this web page. So there's the carrier. It's going to move 5 hertz forward and then 5 hertz back. So that's the same as we got before. If we try to 20, it should go to 25 and 15. And it's there 25 and 15 from them. Okay, and the last method that we have for transmitting our binary digits is phase shift keying. So with phase shift keying, what we have is a number of phase shifts, such as between 0 and 180. So let's find our code. Here we are. Okay, so it's quite similar. I'm defining here 180 is in degrees, but then I convert it back to radians with this. So we'll just copy and paste this bit. And we should be able to see our phase shift keying. Okay. And there we go. So a 1, and then we see the phase shift 180 degrees there, and then 180 degrees for the 1, and then a 0. So whenever we get a change from a 1 to a 0, we see the phase shift. The fundamental is about 10 or just around there, and because we have a 10 hertz signal here. So again, we can have a look at that one. This is our phase shift keying. There we go. This is 1, 1, 0, 1, 0. And here's the lower frequency. And there it is. Okay, so for the final part of the tutorial, given some Python code here which implements this. So you should be able to take this code and then pass in some parameters and produce the same graphs that we have here. Okay, so that's been an introduction to modulation techniques.